Hello everyone. Today I'm going to present General Relativity with the headlights on, number 4. And like in the previous videos, we are going to, I'm going to allow myself only 4 operations of general arithmetic, which is plus, minus, multiplication, and division. Now why am I doing that? Well, I've noticed in other treatments of this subject, it seems as though it's a mathematical focus. And I've looked at Einstein's original works, and where is that? Oh, where's my little book? Oh, there it is. Oh, my big book. Which is the meaning of relativity. And I have the 1956 version. I have to keep gluing it together. It's falling apart now. Anyway, in that, even that's a mathematical treatise. But when you read about Einstein's actual life from biographies, you see that he's thinking in images and thought experiments, and he spent years pondering ideas, and other people say that he wasn't the highest caliber mathematician in the world, far from it. Yet he was able to discover results that other people didn't see. Um, and I think that the clue to this is that he's using other ways of thinking about problems, which are largely have to do with images. And what typically seems to happen is they create these images, and they work with the different aspects of mentation, other sides of the brain, and working in concert with writing expressions. And finally they get the expressions right. But they've had some very good thought experiments and images along the way. And I liken it to putting a ladder up against the building, and they climb up the stairs of the ladder. And I think a lot of that is visual processing. And then when they get to the top, they pull the ladder up, and, and they call out to the people, "Hey, I'm up here. Come on up, join me." And the only way they allow them to join them is to do the mathematics without the many images and many of the less direct but more facilitating thinking. So I'm forcing myself to not use the mathematics, most of which I'm very familiar with anyway. I've studied engineering, advanced degrees in electrical engineering and mechanical engineering also. So I've purposefully restricted myself to the most basic arithmetic so that I can, calculate numbers and that sort of thing, that we can calculate numbers, useful numbers. But basically, in inducing such a tremendous restriction in a subject which is generally taught as being advanced calculus, differential calculus, largely having to do with derivatives, not allowing myself to use even a single derivative. It's a very severe restriction. It forces a person, in this case myself, to use other avenues, other linguistic forms, basically create them out of the mind, and it's really an experiment. And I set out this course, and this is video number 4, and I thought I could get through the end and create with fidelity, that is with a one-to-one match with what Einstein did, but without the complicated arithmetic. And this would achieve 2 basic things. First, if successful, it would provide a more direct avenue for people that don't have a lot of the arcane notation and frankly probably don't want to learn that kind of language. It would provide a very direct avenue to understanding this fascinating topic. And the other reason was it would force me to have to innovate and create images and facilitating images and other ways of looking at this subject. And as I said before, earlier, I would be very interested in, after having completed this, and I'm very close, this series, I would do another series where I focus on the mathematics, but I will use what I've learned in this first series to explode the mathematics and get at the guts of it and make it look, I like to make it look ridiculously simple whenever possible, to make it more approachable and to really talk about the subject we love, which is, I think, more the physics of it than the advanced mathematics of it for most of us in any case. So with that, let's proceed here. And I start, here's a page right out of, what is it? I think it's page 87. I have to move my image. Yeah, page 87 out of Einstein's work, The Meaning of Relativity. And this was his 1956 edition. And first of all, let's read the text and see and this book here, before the appendix for a second. Okay. It's only funny, I can't see the page numbers for some reason. Oh, no, oh, there it is, 107. So it's only 107 pages long, and this is at page 87. So well into it, he tells us something quite fundamental. And I'm just going to read it. It says, we must next attempt to find the laws of the gravitational field. For this purpose, Poisson's equation of the Newtonian theory must serve as a model. So what he's saying is that Newton's theory worked very well for low speeds, close to zero speeds compared to the speed of light. And so whatever theory they come up with for general relativity, it would have to match the results of Newton's theory, and basically reproduce Newton's theory for low velocity and relatively small masses. The Earth, cosmically, the Earth is not that large a mass and doesn't create that large a curvature of space-time, as it turns out. So Newton's theory should be reproduced within general relativity. And he gives Poisson's equation. And it's interesting. I put Poisson's equation here. I hope you can see the cursor. I made it larger this time. I'm very happy about it, to get it large. Anyway, it's the derivative squared there, that upside down triangle of the potential is equal to 4 pi g times the mass density, or the energy density. When C is in balanced units, mass density and energy density are the same thing. But I'm keeping C using traditional units, meters and seconds, which are not balanced. In any case, we see it's a little interesting to me that, first of all, he's not using the symbol I'm used to, and most other people, with the two triangle points on the top. He's using another one with a point on the top. And he's not using a square, so he's got some other little equation I'm not familiar with. I'm going to go over here anyway. I promised myself and you, and I'm holding myself to it, that I'm not going to discuss mathematics. So I just mentioned this really by name. I'm going to do my own derivation on the side here. It's like, Fermat when he was writing that little thing on the side. The margin. I'm going to do that. But let's continue. So he's saying we need to be able to build on Newton and expand Newton, and it must serve as a model. It says, continuing, this equation has its foundation in the idea that the gravitational field arises from the density, and he's using that symbol some kind of Greek symbol of P, of ponderable matter, which means matter like holding a rock, that kind of matter, the earth, our bodies. Okay. In place of the scalar density of matter, which means it has no direction of motion, scalar is just the amount. So 1 kilogram. You say which direction has it? No, it has no direction. They call that a scalar. In place of the scalar density of matter, we have the tensor of energy per unit volume. Now, earlier, in fact, right away, I showed the equipment of my design for measuring that you could build in your garage, very simple, for measuring the inductance of the vacuum and for measuring also the inherent capacitance of the vacuum. And then worked out what those values are, and you can measure them. You do measure them. And these values of the vacuum will apply to any vacuum, no matter how you're moving. For example, if you're in a rocket ship, and more you see people with Elon Musk flying around in rocket ships. You're in a rocket ship, you open up the window with your suit on, of course, and stick out your meter and measure the inductance and the capacitance of free space. It's going to be the same for that rocket as it is for us here on Earth with a vacuum, because it's the same vacuum. So what we find when we do that is that you model it with a circuit and give it an impulse like a voltage spike, and the electric circuit that you're modeling the vacuum on with the same inductance, same capacitance will oscillate at a rate that has the waveform advancing at close to 300,000 meters per second, which is the speed of light. So we see that from this, that all waveforms traveling in the vacuum will travel at the same speed, and it's a speed in which the distance traveled is equal to the time traveled, which means that every wave in the vacuum must be basically traveling in two different directions. It's traveling equally in the time direction as it's traveling in the distance direction. That turns out to be a very, very deep and very, very fundamental and powerful idea, that motion in the vacuum is inherently two-dimensional. Now, we look at the Earth, and we're standing on it, and not moving with respect to the Earth at any appreciable speed, namely a speed very close to zero, so let's call it zero for present purposes. And we are both traveling in time along with the Earth. And so we don't see the other motion when it comes to the Earth, or any other ponderable matter, to use Einstein terms, that we hold in our hands. So with respect to the Earth, we only move with it in the direction of time. So that's a one-dimensional movement. Now, as we're going to talk later, that one-dimensional movement is what Newton was measuring when he would drop a rock from a height, and that only picks up any distortions in the time direction. So it's basically one-dimensional. Whereas in the more general sense, as the speed gets higher, like the speed of a wave traveling through the vacuum, and ultimately we're all in some way, some very, very real and tangible way, we are all composed of waves traveling at that same speed through the vacuum. So namely traveling through two dimensions, the dimensions of time and the dimension of some combination of the other three spatial vectors. So if you were lining up with a particular coordinate system in space, you might be going through time or through x, or if you're going in the orthogonal direction, a right angle to that. You might be going in the direction of time and the direction of y, or if you're again lined up with that coordinate system, you might be going in the direction of time and in the z direction. So in all those motions, it's inherently when aligning to a coordinate system, two-dimensional. So Newton was dealing with the one-dimensional transit. Einstein's dealing with two-dimensional motion, and we'll see that that plays a tremendous role in extending Poisson's equation of Newton. We'll see that coming up. Okay, let's continue here. In place of the scalar density of matter, we have the tensor of energy per unit volume. And the tensor is actually a two-dimensional, has two-dimensional motion in all the components, reflecting the two-dimensional motion of waveforms traveling in the vacuum. So they call that, and again, I don't want to get into it before, I promise I wouldn't, but it's a rank 2 tensor. But the rank of the tensor itself for matter and energy is due to the dimensionality of waves traveling in the vacuum, which is inherently 2. And interestingly, as we're going to see, space-time itself has a 4-dimensional degrees of freedom. It's a 4-dimensional thing. So we have motion, which is 2-dimensional, and space-time, which is 4-dimensional. And we're trying to relate the two together, and that plays a key role, as we'll find going on in this presentation. But let's continue talking about. Einstein didn't say that, but this when you limit yourself so you can only use arithmetic, basic functions, you have to start thinking about other things, and this is the sort of things that I'm talking about in this presentation. So okay, so in place of the scalar density of matter, we have the tensor of energy per unit volume. So he's going to expand Newton's one-dimensional motion theory to include, not to eliminate the one-dimensional motion, because it works just fine under those conditions, but to expand it to consider two-dimensional motion, which is inherently tensorial of rank 2 for 2 dimensions. In the latter, included not only the tensor of the energy of ponderable matter, but also that of the electromagnetic energy. So here we are, late in his theory, like page 87 out of 107, and in his theory. But early on, because this was originally written, I think, what was it, something like 1927 or something. I have to look, if you don't mind. Today I'm trying to get really close, sort of intimate. I'm not too worried about the presentation. Copyright 1922, and the one I have is 19. I think I'd learn how to do that after a while. Yeah, 1956 is this version, but it's 1922 original publication. So anyway, and he's talking about the need to consider the energy of ponderable matter and the energy of electromagnetic energy in the tensor. And then he goes on. We have seen indeed that in a more complete analysis, the energy tensor, the one he's producing, can be regarded only, so only, regarded only, not regarded some other way, can be regarded only as a provisional means of representing matter. So he's saying he's not happy with it. And if he's not happy with it and he created it, we also really should acknowledge that this is just provisional, it's preliminary, and ready to be updated, and not be dogmatic about it. But I'm trying in this presentation to maintain fidelity with his original work here. I'm not trying to innovate, except linguistically and visually. We have seen indeed that a more complete analysis of the energy tensor can be regarded only as a provisional means of representing matter. Now he's saying, in reality, so he's got some other avenue of understanding because his tensor he's saying is a provisional, it doesn't provide a complete story. So he's saying in reality, matter consists of electrically charged particles and is to be regarded itself as part, in fact, the principal part of the electromagnetic field. He's saying that matter is the principal part of the electromagnetic field, and he's saying that's reality. So he's got some other way of thinking about things beyond this current mathematical view, which unites, well, basically expresses the electromagnetic field as in terms of matter. And it goes on, it is only the circumstance that we have not sufficient knowledge of the electromagnetic field of the concentrated charges that compels us, provisionally, compels us, because otherwise we'd want a more explanatory view, to leave undetermined in the present theory the true form of this tensor. So what Einstein really wanted to do, first I'll just add, he was key, one of the key people in the development of quantum mechanics, but he was never happy with it because it dealt with probabilities, not certainties. And Einstein hoped that if he could just unify the gravitational electromagnetic fields together in one theory, that he would also fundamentally have to revise quantum mechanics. And he hoped, and he indeed, since relativity is a classical macroscopic theory and deterministic, he was hoping that the resulting a new ideation of this theory, combining electromagnetism and gravity, would also revise quantum mechanics and make it more deterministic and a bit of a more acceptable form. And Einstein was trying to get to this, and I find it very interesting. And this mentioning that we need to build on Newton's Poisson equation is also turns out to be very, very fundamental, and it was actually key for me to be able to develop pictorial, visual, and not complicated, very simple arithmetic level of understandings of this theory without having to go through all the differential calculus. So I found that very helpful to me as well, building on Newton's theory. So let's go. I mentioned here, well, Einstein mentioned it, so I had to bring it up. But I'm going to get out of that over here, and I'm going to derive this Poisson, what they call Poisson's equation, this little fish. Poisson's equation. So here I have over here Newton's theory. So we start out with what you've probably heard before. I'm almost sure you've seen this. Force equals mass times acceleration. That's Newton's first law. And in terms of gravity, it works out to be the force is m1, m2, two masses attracting each other, times the Newton's constant divided by the radius between them squared. So force equals m1, m2, g divided by r squared. That's that first line shown by my massive cursor there. You're moving. So now we divide both sides of that expression by that m, the red one. I like to color the things I'm going to divide on both sides a different color that stands out. So we get rid of the m1. So we have a is equal to m2. Notice it looks like m squared. That's a flaw in this notation that Einstein also had. So we'll just put up with it for now. But it's m2, second mass, times g divided by r squared. And the r squared, it really is the square. So the acceleration is equal to m2g divided by r squared. So I got this update thing. Okay, good. I'll be quiet. Got rid of it. Good. So A is equal to m2 times g divided by r squared. So now, that's at one point let's say we had the Earth when we were on the Earth's surface, which is effectively a sphere, and we're at one point. Now, a very good question to ask is, well, what's the total? If we know what the acceleration is at one point, but what's the total? We want to measure some measure of the total acceleration. Well, one obvious way of doing it is to multiply the acceleration at that point by the surface area, the area of that sphere. So we get some kind of measure of the total acceleration. So let's do that. Surface area of a sphere is 4 pi r squared. Multiply it by a. That's what I'm doing here, right at my cursor. And divide by the volume. So we're doing some kind of neat thing. So you take the acceleration, you multiply by the surface area, and then that gives you a number, and then divide by the volume. So you kind of have an acceleration area acceleration density, because you're divided by the area, is equal to 4 pi times, and the reason I did that was there's two steps in this move. We have mass over on this side, the other side, and Einstein over here has mass density. So I have to divide by the volume anyway. So that's where it shows up. So on this side of this expression where my cursor is we have 4 pi r squared a divided by the volume. But why I had to do that was because I have to take the mass on the other side of the equation and divide it by the volume. So when you divide a mass by a volume, divided by volume on one side of the equation, you've got to divide it on the other side. So that's where that volume on the bottom came from. And then I'm going to continue reading. Is equal to 4 pi r squared m2 divided by the volume, that's mass density, g divided by r squared. So now I notice that on the right hand side here, we have r squared in red, and then divided by r squared in red. Well, I made it the red color again because they cancel. So what we have is, on the reading on the expression below that, where with the cancellation in effect, we have 4 pi r squared times a divided by the volume. And the I is because I sometimes want to talk about initial volume, and it also distinguishes it from velocity. So I always like to use that. So V sub I is for volume is equal to 4 pi times the mass density times g. So that's basically 4 pi g on the one side. That's Poisson's expression in terms that we can understand. It has no arcane, like as if some sect was made their own notation, private notation. I'm using common view notation, almost no notation. This is saying basically the acceleration area is proportional to the mass density. See, on the one side of the expression you have 4 pi r squared a, which is the acceleration area, and on the other side of the equation you have the mass density. Now notice, mass density, yes. So that's equal to the strain acceleration, because what if you look at a is the acceleration and 4 pi r squared is the surface area, and so what you have is surface area accelerating inward in this case. So it's if you take that, the change in the volume divided by the volume is a strain, but this isn't just the change in the volume, it's the acceleration of the volume inward. So it's a strain acceleration. It's a term I made up, but it is a useful term. Now, it just works out that if you take the strain acceleration and divide by c squared, you get the curvature. And so knowing the strain acceleration is a tangible concept. And curvature can be a somewhat less tangible concept. Although I did cover it in, I think it was video number 3, so you might want to check that out, which I calculated it for the Earth, what the curvature was. So we have another view in this, what we're seeing here. And just remember, I'm talking about the Poisson's expression because Einstein said this is fundamental and we're going to build on that for general relativity. And I don't necessarily appreciate the mathematics used, so I'm expressing it in a more transparent language. And I'm telling what it says. And it's basically saying that the strain acceleration is equal to 4 pi g times the mass density. Now, that's good, but strain acceleration, we can understand that. But if you divide by c squared, it becomes the curvature. So, wow. So this little expression by Poisson used by Newton, he's already talking about curvature. The curvature of time in the time direction. When you look at these fancy little terms, you go, oh, great, and you go on and you solve the problem. But you may and probably don't have a deep understanding of what the hell's going on. When I just look at this and I just wrote this like it's my kind of language. You just write it out simply. And then put it into words. Put it into words exactly. I don't want metaphors here. And if you do have a metaphor, I want to follow it directly with something that's exact. So here we go. This 4 pi, and then k here is Newton's gravitational constant. So it's 4 pi g. 4 pi g, if you divide by c squared, you get curvature here. So I'm continuing on. 4 pi r squared, then the green down near the bottom there, on the margin, left-hand margin. 4 pi r squared a divided by the mass density divided by c squared times the, I don't need the, times the volume. So I just took mass density, put it down there. That'll work. That's equal to the curvature divided by the mass density. And it's equal to 4 pi g over c squared. Curvature divided by the mass density is equal to 4 pi g over c squared. What that is saying is that it's kind of like a bulk modulus here. It's saying that the curvature divided by the mass density is a constant. 4 pi g divided by c squared. C squared is constant. G is a constant. Pi is a constant. And 4 is a number. It's a constant. Okay? Now, over on the other side, the curvature is a variable, and the mass density is a variable. And the ratio of those two things is a constant, which means if I increase the mass density, the curvature must increase commensurately. So this expression applies to the moon, it applies to the sun, it applies to the earth. This is a freaking amazing statement. So I'm looking at this thing that Einstein writes as a squiggle, and I can't even make out, because it should be, in my view, it should be that symbol squared. Anyway, it doesn't even make sense to me. But even if it was written in modern terms, like I wrote beside it, it still wouldn't provide the message. It's only because I've been doing this without allowing myself the mathematics, that I can see what the mathematics is saying. That's another beauty of this method that I just forced onto myself, like some kind of masochist or something. It wasn't easy to hold to that rule, just use basic arithmetic, but it opened up so much. So here we go, and it allows me to see that Newton's work, if you got rid of the math arcane notation and focused on what it was saying, it's saying that the curvature divided by the mass density is equal to a constant, and we have the constant here. It's basically a baby version of Einstein's general relativity. So, however, it's for one dimension, which means it's 4 pi g over c squared. Now, you might ask, well, what about if it was dealing with a waveform going through the vacuum? You'd pick up the replete effect of space-time curvature on the waveform, rather than picking up only this one-dimensional view when you're traveling along with the motion of the object. So like we are on the Earth. So we don't really put that motion into effect. But when a waveform, it travels the distance through time and the same distance through space, through distance, time, and then also one of x, y, z, or some combination, but still one vector, one direction. So inherently two-dimensional. So Newton had this one-dimensional view on the problem, and it was inherently a form of general relativity, even though Newton didn't realize it because he was doing the fancy math without thinking it through enough. It begs the question: what about if you look at the full picture of this curvature and this mass density, which is what Einstein did, and it is a direct extension upon the work done by Newton. Once you get rid of this obfuscating symbology here, a triangle with a, looks like, what is that? Some kind of a donut with a stir stick through it or something. I don't know. Let's go here. Well, so we continue on. Boy, that was quick. Okay, so I'm showing you here again. This is a diagram I worked through in video number 2 and video number 3. You might want to look at it again. And I bring it up because I need this. I need the boost. I need this relativistic boost, which is basically 1 over the square root of 1 minus v squared over c squared. Let me say that again. 1 divided by the square root of 1 minus v squared, the velocity squared, over c squared. So it's a ratio of the velocity divided by the speed of light, all squared, and that goes in, and then 1 minus that, they take the square root, put it on the denominator, put 1 on the numerator, and that's this, what in my diagram is basically just the green line h divided by the length of the red line O. I don't want to go into that today because we'll get bogged down, and I do a very good job in videos number 2 and number 3. But I do need that relativistic boost, and we call it gamma. Let's see, up. Gamma goes down and around, and then up, down. Oh, wow. Down and around and up. Well, I can't do it on the screen. But look it up, gamma. I think it's Greek. I don't know. Could be. I think it's Greek. So anyway, you might want to review that. And here's a diagram I use. Oh, there's gamma. There's our friendly little blue gamma. You can see it goes down and around and then up. And move myself over a little bit. It seems I'm creeping over all the time. I don't understand why that is. I'll move my presentation. There we go. Like I said, on this one I'm trying to get a little bit more intimate so I can express these ideas without just rushing through it and say, boy, I did a great presentation. Great for me, yeah, but what about for you? We need to slow things down a bit, let them sink in, and talk about what they really mean here. Anyway, there's that boost factor. And what I do basically, and uh, I take our motions, and they're all arbitrary, and they're in force space, so I throw them down, and I let them cross at a point, in this case H, because you need between these two momentum lines. We're riding on the green line, so we don't even notice the motion we have in the green direction. That's our time direction. We express it as time because we don't notice it. We're riding on the thing. It's like, what's the speed of your car when you're in your car? It's just, you look around, you drink your cup of tea, and basically it's like your car's not moving. You look outside the window, everything else is moving. Well, that's what it's like on our green line. We have time in the direction of motion rather than space as we're moving through inside our car, and that is while we're riding on that green line. And then somebody else is riding on this blue line here, which is going in its momentum traveling in a different direction. Why should it travel in the same direction? And in general, there's two arbitrary directions. So, but I have them cross at this point H so that they can synchronize their clocks. And that's important because when two clocks are synchronized, then you can measure the time, see how the time tracks. And you do the whole thing, which I did in video number 2 and video number 3. So but I need that expression. Here I actually wrote it out. Gamma, which is what we call the relativistic boost because it makes it bigger, is 1 divided by, in brackets, which is the square root, 1 minus v divided by c squared. And then you take the square root of that. So that's the relativistic boost. We need that. I only bring it up because we need it. Okay, so I'm reviewing a few things here from previous presentations. So here we have K. We demonstrated in presentation number 3, and I'm going to prove it coming up. And when you get to this level where you've gotten rid of the obfuscating mathematical notation, the arcane notation, that is very helpful. In fact, I'm actually craving to use it. And not being able to use mathematics is quite a severe restriction. But it forces the mind to come up with other ways of thinking about it. And those other ways are, I think, just as useful, and I think in many ways more useful than having the notation of arcane notation of mathematics at your disposal, like in your toolkit. So here we have what we just derived from Newton's Poisson expression, except the value is double because we're talking about motion, two-dimensional motion. The vacuum waves traveling through the vacuum media, and we've discovered but we didn't really, we worked it out, but we didn't really prove it in presentation number 3. But it's key. The strain A divided by the stress is equal to 8 pi g over c squared, and then the stress divided by the strain, which is the inverse of that, is equal to c squared over 8 pi g. So this applies when you're talking about mass densities. The units are kilogram per meter. So it's having to do with basically how you convert mass density into the strain acceleration. And if you divide by c squared again, you get the curvature. So we'll deal with that more. But this is Einstein's constant. Now I have to talk about it. It's Einstein's constant, and here it is. And when you want to convert mass density to curvature, you multiply by one of the forms of K. We'll talk a bit more about that. And I did talk about it already in presentation number 3. So you multiply by K times the mass density or the energy density, in which case you have to put another c squared on the bottom, c to the 4th. So you multiply the strain acceleration divided by the stress, which is that constant, times the mass density, and you get the strain acceleration. And if you divide by c squared again, you get the curvature. So this is the key that allows you to convert mass density or energy density into curvature. And when you invert it, you can multiply it and you can convert curvature back into mass density. So this is like the universal translator of general relativity, translating between mass density and curvature. The whole thing hinges on this. I know it sounded boring there for a second, but when you think about it, holy cow, it's powerful. And we have a little more to say about that. I also, here I'm showing, if you want to convert matter, use 8 pi g over c squared. And that's the curvature divided by the mass density. And then if you want to work below here, I talk about if you want to convert energy density, you got to put another c squared on the bottom, because it boils down to E equals mc squared, so there's another c squared, and when you go through all the math, which I've done 100 times, you have to make it c squared on the denominator, not c the fourth on the denominator for energy density, c squared on the denominator for mass density. And that, of course, can be inverted as well. Okay, and the units of K for energy density is seconds squared divided by meters divided by kilogram. Now, I've said this before, it's so convenient to talk in terms of balanced units, where the distance traveled by light in time is equal to the distance traveled by light in space. So that makes c equal to 1, and c squared and c to the fourth all disappear. Now, why I don't do that is because if you keep c in there, it's so difficult. You're always tripping all over yourself, and it provides another avenue for you. Actually, so many different avenues for you to make mistakes and start talking nonsense. So I use it as for two reasons. One, it's an error detection mechanism to find out when you're confabulating, because it all has to work out if you keep C in there. And also, I think probably more importantly, the direction C, if you're going, if you're pointed in the direction C and you're traveling in the direction C, that tells you the directionality of the motion, and I find that useful too. So I keep C in there, and it helps keep me honest, and keep it hopefully without errors. And then this is a review as well. We went through and we calculated that the value of the K is for converting mass density is 1.863. Here I'm reading in the green on near the bottom here. 1.863 times 10 to the minus 26. That's pretty small, and the units are meters per kilogram. So we have a match for the numerical value and the units, and we know what it represents. That's a very powerful position to be in. Now, I want to throw something out there. I think it's good to stimulate people's minds. Maybe not everybody will be stimulated by this, but there's quite a few people out there that when you show them something like this, it makes them start thinking, and they can't get it out of their head. And one way or another, they're going to discover important things, maybe not related to this, but in their many sleepless nights and tossing and turning and thinking about this, trying to get at it, they might discover something else, or I would say almost for sure. So I'm putting this out there. We determined that the ratio of the space-time curvature to the energy density is, now energy density is going to be another c squared on the bottom there, so it's going to be a different value than I described. The value of this number, the curvature to energy density ratio, is 2 0.07 blah 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 times 10 to the minus 43. It's very tiny. So it works out to 2.0762 thereabouts times 10 to the minus 43. Okay, that's a small value. That means that the curvature, you need a lot of mass to produce any appreciable amount of curvature. And I also talked about this in video presentation number 3, where I worked out the curvature of the Earth and the radius of curvature. You know, for a small radius, it's really tight curvature. For large radius, it's, you know, seems like a straight line. Well, the radius of curvature of the induced by the mass density of the Earth at the distance of the radius of the Earth, surface of the Earth, that is, the curvature induced by the Earth on space-time has a radius of curvature that's 2/3 away from the Earth, the distance between the Earth and the Sun. So basically almost straight, almost impossible to measure, although I think they can just barely measure it today. They use other methods like seeing how light grazes as it goes close to a star to get a more precise measure. Anyway, it's so small it's hard to measure even under the best of circumstances. Anyway, and point 2 here, the ratio of the gravitational force to the electrical force is 2.415 times 10 to the minus 43. Also, so one of the things that people like myself get tortured with is, I say tortured, but you know, mentally trapped thinking about it, is why is it the ratio of the electrical force and to the or the ratio of the let's see now, I have to think about what I'm talking about. The gravitational force and the electrical force is 10 to the minus 43. Why? Well, here I have the ratio of the curvature to the energy density is also 10 to the minus 43. So the lights start lighting up here. And then, well, then you think, well, maybe the numbers, the the actual number, not the exponent, is not close. So I compare the numbers, 2.0762 and then 2.415. So we already know there's a relationship between curvature and the gravitational force. So that part, the two numerators are definitely related. And then it makes you wonder, well, is the energy density, the denominators, the numbers are so close, you would expect the denominators also to be related. So I look at this and it begs the question, because they're within 16% and over 10 to the minus 43. So there's probably something in there, but I haven't spent the time to pursue it, because I'm talking about general relativity at this moment. Earlier in this presentation, we showed how to construct two simple apparatuses. One to measure the induction of free space, which is the vacuum, and another to measure the capacitance of the vacuum. And these were two simple pieces of equipment that could be made in your own garage. And we determined exactly what the inductance and capacitance of the vacuum is. And modeling that circuit with the same inductance and capacitance, we show that the speed of any waveform propagating within the vacuum must travel at a particular speed, which is approximately 300 million meters per second, or 300,000 kilometers per second. And also at this speed, the waveform will travel exactly as far through time as it does in distance when you balance the units, which are ordinary units in meters and seconds are made to fit the human experience, not to balance the physical truth. But we're using those because of familiarity and other reasons. And now here's the most important part. Now we're actually beginning to piece together the gravitational field expressions. And we're purposefully trying to demonstrate complete fidelity to Einstein's model to show basically that we understand it. However, I'm imposing upon myself the need to not use fancy mathematics and to limit myself to mostly purely physical reasoning and use images and simple arithmetic to come to the same conclusions, but through innovative methods that I think allow a more direct perception, because you're not relying on the backbone of the mathematics to produce the results for you. You have to produce them through your own perception. Um, and then to Einstein used a particular notation where he defined the time coordinate as x4, whereas I've been using it as x1, and on purpose. And he also defined x4 to be the complex number I times the speed of light t times t. And that's following Minkowski's work. And we've been using x1 as defined as the speed of light times t time. So it puts it on the same footing as in our diagrams. So the units are naturally balanced when you make a geometric diagram. So and this gives us the same time as we're using on our clocks rather than complex time. Now let's have a look at what we hear that, or at least I used to be taught that the square root of that I is equal to the square root of -1, and I never liked that because it seemed a little illogical. However, when you interpret it as operations on a plane, it becomes very, very logical and intuitively makes sense and very useful as well. So I'm going to show you what that looks like. So we have here an arrow going up, pointing up in space, and some people, let's say somebody says, "Oh, it looks like it's an arrow, it's a vector, I don't understand it." Well, remember what's that Nacho Libre when the guy got shot by an arrow? I mean, at the moment you get shot by one of those, in this case, toy arrows, you immediately understand what a vector of momentum is all about, So we have an arrow A pointing upwards, and we operate on it with the symbol I, and it's a 90-degree rotation. I don't like to use the degrees, but let's say a 1/4 complete revolution to the left. By convention, it's to the left. And so I like to think of you come to a 4-way stop in your car, and you turn left. Now you've done a physical operation, and we all know what that means, turning left, and it's a quarter turn to the left. And this is the operation I, but it's very tangible, performed on a real car. And that's the way I like to think about it. Keep everything tangible, as tangible as possible. And then it's like, well, what about the square root of -1? Well, if you look and you do another I, so you do I times I, which is I squared as an operation. Look on the right-hand side, this one. You do a 180, and we all know what a 180 is. It's a complete reversal. So you could say that I squared times that A is equal to -A. So it's kind of like a -1, but it's an operation on a plane. It makes sense there. It's not a, let's say, a single number operation, at least not in any way that I like to think about it. So we understand I. Have we finished there? So yeah, for when we're looking to see if we can match with Einstein's expressions to check for fidelity and correctness, we're going to use his notation because that's what he used. So that all makes sense. So here I'm going to read this, mostly read it because I want to get the language completely correct. And we are opening the door, and we're getting ready to put the pieces into Einstein's gravitational field expressions, and we're not using fancy mathematics, so at least I have to use some accurate, language, English language here. So let's talk about it. Newton's theory works accurately at low speeds and smaller masses, such as the mass of our planet Earth, which cosmically is not large enough to curve the space-time to a degree where we wouldn't consider it essentially flat. So it's essentially flat. And this necessitates that our gravitational field equations must also converge with Newton's theory for low masses and low velocities. At low velocities, masses travel almost exclusively in the time direction, so it's a one-dimensional. It picks up the curvature in one dimension because it's only transiting through one dimension. But in when higher speeds, and in the more general case, or propagations, waves through the vacuum, will, as we've shown by modeling it with our electric circuit and using the capacitance of the vacuum and the inductance of the vacuum as measured, we find that the waveform goes in equally in distance in the time direction and in the spatial direction. So as a consequence, we have to be able to start with Newton's in the one-dimensional situations, one-dimensional transits, and be able to migrate towards two-dimensional transits. As a consequence of this unification, we will also completely derive and define Einstein's constant K, which relates force space curvature and energy density. So using Newton's theory for low speed, where masses travel almost entirely through time, and in here we see, I'm going through, and I'm not going to do this again because I've done it recently in this presentation, but you go through and easily derive Poisson's expression. That's what we do here. And we come up with 4 pi times the mass density times g is Poisson's expression, 4 pi r squared. And where a is the acceleration. So we have that the acceleration times the area is proportional to the mass density. And at low speeds, we have that the strain acceleration is equal to 4 pi g times the mass density. Now, strain acceleration, the definition of ordinary strain is where you put pressure on a piece of metal or something, and in this case a sphere, and the sphere contracts under the pressure, and it's basically to a very pretty accurate enough that it's the surface area of the sphere. And since it compresses a small amount, you can just say it's times the distance of the change in the radius. It gives you the change in the volume. And you take the change in the volume and divide by the volume, and that's by definition what a strain is, right? Now, in this case with gravity, the volume is not only, it doesn't contract once and then just stay there. If you put a shell of small particles, the volume of the small particles will accelerate inward. So you call it a strain acceleration, and that's what we're measuring here. So we have that derived several times in the last several charts, that the detected curvature divided by the mass density is equal to 4 pi g divided by c squared for low speeds and smaller masses as per Newton, because in Newton you've got masses and you're moving Well, in the case of the Earth, we're standing on it, and we put particle out there with a velocity rather, initially 0, and it'll then, in this relative to us, travel exclusively in the time direction. So that was what Newton was measuring and what he built his model, his theory on, and it's correct within that scope. So we just described the low speed result from Newton, and it is not the same for general relativity. In general relativity, we must accommodate larger masses and higher speeds. We know that at higher speeds approaching the speed of light, roughly as great a distance through space is traversed as through time. And this means that the curvature through a space transit is experienced almost equally to that of the curvature through the time transit. And the fact that space and time are curved equally by an energy density necessitates the high-speed curvature of these two-dimensional transits, like through time and through space, will be exactly twice that from the one-dimensional transit that Newton was measuring. And this proves that in general relativity, the curvature divided by the mass density is equal to k, and that's equal to 2 times the 4 pi g over c squared that Newton got, and that's 8 pi g over c squared. And this means that light must fall near the Earth at an acceleration of 19.6 meters per second, which is twice the acceleration that we experience by holding up a rock and letting it travel, which is what Newton was using, mass as the detector of the gravitational curvature, and not light, for example, or not a waveform traveling through the vacuum. We have tested this and found that it's true for light. So we just proved that the two-dimensional curvature is given by the curvature divided by the mass density is equal to k. That's equal to 2 times 4 pi g over c squared. And that's for mass density. If it was, and we've discussed this earlier, if it was energy density, it would be 8 pi g over c to the fourth. And where c is balanced, in balanced units, c is equal to 1, and it's just 8 pi g. So, but we're not going to do that here. This means that light must fall near the Earth at an acceleration of 2.6 meters per second squared. This is for continuity with what we just said before. As the relative speed increases, GR, general relativity, thus transitions progressively from Newton's one-dimensional curvature to the two-dimensional curvature experienced near and at the speed of light. So it's not just light that goes equally in distance and time as in space. And anything even close to the speed of light goes effectively, and like mass particles, goes effectively equally distance in space as in time, and will experience this 8 pi g or divided by c squared rather than Newton's 4 pi g over c squared. So it also, these mass traveling that quickly will also fall in a gravitational field at twice what the acceleration that Newton predicted. Now, this is not all that exotic, because even when in the television sets that many of us grew up with, the cathode ray tube, and earlier also computer screens, they had a cathode ray and they accelerated electrons in the magnetic field, electrical field and magnetic, and got them up to very close to the speed of light. And those electrons were while they're traveling, were falling at twice the rate that Newton would have predicted. So this is very real and very tangible. So, we're just talking about transits through one dimension of in this case, time, and transits through time and space, and the transit dimensionality, the effect that has on the acceleration experienced, and basically the curvature of space that is detected. And a key point I'm going to make right here, and it's written down so I don't forget it. This is quite a separate phenomena from the total four-dimensional curvature, because mass curves space it curves the four-dimensionality of space. So there's a curvature in each of the dimensions, each of the four dimensions of space-time. Now Newton, but that's not the same as what you detect. Newton was dealing with relative motion of masses transiting straight up through the dimension of time, and only picking up the curvature in time using that mass as a detector. And in general relativity, we do accommodate that. But for the other transits, such as higher speed transits, for waves moving through the vacuum, and for what we identify as mass particles moving near the speed of light, you go through time and space equally or more equally, and you get twice that amount. But there's not, to my knowledge, a way of traveling in four dimensions at once. I once told that story about when I was rollerblading in a direction and my daughter was being attacked by a pit bull, which I was not very happy. And I really tried all my might to go back, traveling like two directions at once, but I ended up falling on my belly. It's a graphical example of the reality that that we, when we align our axis to our direction of motion, we're only going in one direction at most, in space and time, and maybe in another direction. So two directions at most. So this is quite a separate phenomena from four-dimensional curvature. Four-dimensional curvature exists but is not directly experienced by our two-dimensional motions. Consider that we have shown that a wave traveling within the vacuum must travel equally in time as in space. This is intrinsically a two-dimensional motion. However, our universe macroscopically can be described as a four-space. Thus, when describing the curvature in this four-space, we'll have to capture the total curvature. So there's two metrics, two measures that are quite different. One is the curvature we can actually detect, and the other is the total curvature, which we can detect by, I'll show you the method for detecting that, but it's not going to be done with a single mass, not at once. I mean, you're not going to experience it at once. So when relating curvature to motion, we will have to describe how the four-space curvature is translated into two-dimensional and even one-dimensional relative motion. This is the true function of our gravitational field expression, as we will make evident shortly. So I'm going to start talking about the piecing together the relativistic gravitational field expressions. And we're looking now at the stress tensor portion. And there's two basic ways to express the relativistic field. One, we can evaluate a single swarm of particles having specified rest mass or energy densities moving relative to an observing frame. So two frames, one the particles moving, and the other one, well, one is in the particle frame, they won't experience any motions because as a reference frame. But in the observing frame, the swarm is moving, so it has let's say a four-dimensional momentum, four components of the momentum relative to the observing frame. So in relativity, everything's relative to who's taking the measurement, or what's the machine what's the relationship between the machine taking the measurements and the objects being measured, what they're doing. So the second way is of expressing the relative field is to put the values for the relative mass or energy densities, put in the values for the relativistic mass or energy densities, and perhaps later work out the rest masses or energy densities. And this is what Einstein did in his field expressions. An approach greatly simplifies the presentation because you're not going to have to put in the Lorentz relativistic boost factors and the inverse of those. And there's a lot when you have to look from the observing frame or and convert rest mass and rest volumes and from the other frame, the frame of the swarm of particles. So we'll look at both of those and they'll start to make more sense. So first we're starting with evaluate a single swarm of particles moving relative to an observing frame and the particles have a four components relative of 4 components of momentum relative to the observing frame. So it's very important here that we pick everything into a picture. So because I'm not relying so much on the words as well. The words and the images work together. So let's look at this. So we have we in our measurement equipment are traveling arbitrarily along this green line, and then we have this swarm, which I've shown here. It looks like a swarm of bees, trying to find a place to make a nest. They're traveling in an arbitrary direction, having 4 components of momentum relative to the green timeline. And what happens there is the particle swarm has a rest mass, but from the perspective of the person traveling and the equipment traveling on the green line, they pick up the relativistic mass, which is the rest mass boosted. And also the volume, the initial volume there is contracted. It's contracted by the Lorentz contraction, which is 1 over the relativistic boost, which is that gamma. Now, the volume then gets multiplied by 1 over gamma, the relativistic boost, and the volume is in the denominator. So when you divide the denominator by something, it comes up onto the numerator again. So you get the boost converting the rest mass to the relativistic mass, and the rest mass is Q here. I'll define it more deeply in the next chart, what this swarm is. But making this point about why you need these 2 boosts multiplied, so it's a gamma squared. Well, the first gamma is to convert the rest mass to the relativistic mass. And the second gamma is from the Lorentz contraction of the volume, because we're talking mass density here. So you get gamma. You're going to have gamma squared. Yes, sir. So here we have. I want to talk about this mass density times 4 velocity components equals the 4 momentum. And it's the number of particles and the 2 gamma boosts, which is going to be gamma squared, times the particle rest mass. So you get the number of particles times the particle rest mass times gamma squared divided by the volume times the 4 velocity components, and so you get this gamma squared NQ, which the particle number times the mass divided by the volume times the velocity components. So I'll show you what we do with that, but first we're going to define things a little bit more clearly and more explicitly before we derive the total components of the momentum flux, and we derive the stress. I hate that word tensor, but just to make it a little bit more friendly, stress. It's ordinary stress is a tensor, and when you get out of the bed in the morning and you jump on your feet, ready to go, you feel the stress on your knees and your hips, for example, and those are tensors, which is sound but it sounds so scary but really it's we feel that in our bones every day, and we don't interpret it as anything but completely normal and not exotic. So here, what do we say here? In the previous example, we demonstrated that a flow of momentum across the surface causes a curvature in space-time. So if you that brings up a very very pertinent point here, that when you have it's like let's imagine you have a sign and you're shooting it with a rifle, something that it seems, I don't know why, but people seem to like to do that, especially in the country. So anyway, you're shooting this sign, and the momentum goes through the sign. Well, that's what we're talking about. Perpendicular. The sign is perpendicular to the flow of the momentum, and that causes a curvature in the direction of that the momentum is traveling. And so the word perpendicular comes up because it's perpendicular to the motion. And that perpendicular, for example, if that was a distance in the x direction where that sign was, that's a x constant direction. It's like a cross-section plane where that sign is of constant x, and the bullet is going through that, and that's what that will have the ability to and will curve the spatial dimension in that direction. In this case, I said x, so the x dimension would be curved by that. So very small for a bullet, but when you have a planet like Earth going rocketing and perpendicular to the direction of time, it does have an effect. Still a relatively small effect because the Earth is not that massive cosmically, from a cosmic sense. Alrighty, so okay. So hence, to keep track of all the possible components of curvature in space-time, we need to keep track of all the possible components of momentum flow. And next we'll do that. So the components of momentum can be represented by, and which we derived earlier, gamma squared times the particle number times the particle mass, which are called Q, and particle number n, divided by the volume, and then multiplied by the sum of all the velocity components, 4 components. So here I say, and what's Q? Let's go into that a little bit more. Q is a uniform particle of mass as measured in the co-moving frame. So it's within the moving frame, so it's a rest mass. It could now this is a subtle point, but I'll say it. It could transform from solid. I'm making this like a super particle. It can transform from solid to liquid, to gas, or even plasma, shedding charges, electrical charges, as needed to fulfill all the components of momentum. So when you make this stress tensor from a we're not going to use math, but from arithmetic, we're going to use ordinary multiplication. We'll get it, so in a way that we understand. But you'll have a lot of components there. There's not necessarily going to be anything in that component. It's just representing a possibility, something that, from a cosmic accounting point of view, for completeness in the theory, we have to have a place for that particular specific situation, whenever and wherever it could occur or not occur. So it's a placeholder. And some of these things are harder. There are situations in which you can align your axes. I'm going to show that later, where you can't produce a particular component easily using just mass. But interestingly, if you have charges, these shear stresses, and you'll see later, can be produced. So I'm letting these swarm of particles be able to produce charges or go solid if you need shear forces. The viscosity can be a thick liquid, it can be solid, it can be a gas. So it can serve whatever the requirements we need to fulfill a physical situation. So I'm making it general in that sense. So, and V is the volume containing, a volume within the co-moving frame containing the uniformly distributed particles as measured within the co-moving frame. Okay, so N is the number of uniform particles. Now the number of particles shouldn't change depending on who's observing it. It's an aspect of physical reality, and the number of particles doesn't have a direction or anything. So we call that a scalar, and a scalar's going to be something that in practice is agreed upon in all reference frames. Very useful to have something that's frame independent, and scalars are. All scalars are. So N is the number of uniform particles. Now N over V, V sub I like to put the sub I, I've talked about that before, is initial volume, and it distinguishes it from velocity, is the number of density, density of particles per unit volume. And V with the superscript alpha is the velocity component. So alpha can have components 1, 2, 3, and 4. And I say it's V over C in the direction, whatever direction alpha points. Direction x alpha in the frame which detects the velocity. So the velocity is not going to, it's going to be 0 in the co-moving frame. So when you're talking about velocity and you're going through that trouble, you know that you're most likely in the observing frame. And V total is the total velocity of all the particles in the frame, the observing frame, calculated from all the components. So we grew up taking the components squared, right, and adding them up, and you get the velocity squared of the total, right? Take the square root, and you get the total velocity. And that's important because when you take this swarm and it's moving relative to the observing frame, the volume is squeezed by the same, it's compressed. And that's compressed by the same amount for all the particles, so that it gets the same from all the directions, and it share that same volume. And so the compressed volume affects all of the components. So you need to, and it's not the component volume that affects all the components. So you have to distinguish between the total velocity and the velocity components when it comes to the boost from the volume compression. Yes, so this means that the number density will also be relativistically boosted to gamma times n times v over times n divided by the volume, gamma times n divided by the volume. The total momentum particles current, or it can then be represented in terms of its components as you take the total four-dimensional velocity vector and you take the total four-dimensional momentum, which is, as I just said, we proved earlier, gamma squared n times q divided by the volume times all of the components. That's the momentum. So let's go next. How to represent the degrees of freedom in the table, see below. So as the gravitational field equations have to act like a cosmic accounting ledger. It has to have placeholders for all the possible situations for matter and energy. and which basically when you're talking about possibilities, you're talking about you have to talk about the degrees of freedom, because if there's 16 degrees of freedom, in this case there is, um, under different circumstances in the universe, all of those 16 will be expressed in the sum total of situations. So we need to have places in our expression for that, even though in some situations the values will be zero. It's not like you're going to have everyone have a non-zero value in every placeholder in all the situations. That's not true. So we have 16 degrees of freedom, which is to say 16 possibilities for the components of curvature due to the components of the momentum flow. To be complete, we need to account for each of these 16 possibilities. We can produce 16 possible momentum particle currents by multiplying the momentum particles by the square of the unitary momentum current. Now that's a mouthful, but basically I'm just going to do a multiplication. So we take the and you'll see that it produces all of the possibilities, and that's why we do the multiplication. So in order to represent all the 16 degrees of freedom. So that's a simpler way of saying it. So you take the n times q gamma squared divided by the volume, and you multiply that by all the components, you get the momentum expression, and then you multiply it by the velocity, forward space velocity with the four components. Again, you just multiply that, and you'll see that all of the degrees of freedom are represented. So let's do the multiplication. Now this is the blue arrow there. Just ordinary multiplications. Yes, it is. So we do that. So you get, like an ordinary multiplication, you go, okay, I'm taking the top V1, V2, V3, that's V4, I'm multiplying it by V1, and then V2, then V3, then V4. So I do that. And the term out there, the constant there, gamma squared NQ over volume, that multiplies everything. So I just start with, I stick that outside because, multiplication, what do they call it? Associative, is it distributed? Yeah, I think it's distributed. Whatever, it's just words. You multiply every one of the terms. That's how I think about it. So you put it outside and knowing that it multiplies all the terms. Now, so V1, so let's do it. V1 times V1, and there's a term. V1 times V2, and I'm going on top row here. That's V1 times V2, and then V1 times V3, and V1 times V4. It's just like when you calculate, multiply numbers. It's the same thing. So then you go V2 times V1, V2 times V2, V2 times V3, V2 times V4. And then you go, say V3 times V, I'm going to do them all. V3 times V1, V3 times V2, V3 times V3, V3 times V4. Okay, I got the third row. Now the fourth row. V4 times V1, V4 times V2, V4 times V3, V4 times V4. So now we get the whole thing. So, and then we multiply this term. I said multiply them all. I literally did that. And in the yellow square below, and we get this thing, and we would say, well, what the heck is that? I mean, we understand it, what we did, and we understand that it represents all the degrees of freedom faithfully. And I say here, surprise, we just derived Einstein's stress energy tensor for a single swarm of particles having four components of relative momentum. So, wow, that's pretty awesome. Of course, we're going to have to play with this a little bit to really understand it, but don't worry about that at this point. You basically understand what we did, which is basically an ordinary multiplication to express all the possibilities, and it's all completely understandable, and there it is. So let's see what else here. So I'm reminding everyone that and up here the curvature divided by the energy density is equal to, now notice I've said energy density is equal to 8 pi g, and it's not over c squared, which would apply to mass density. It's c to the fourth in this case. So you have to keep track of whether you're doing mass density or energy density if you're going to use meters per second for the speed of light. So let's revisit why light experiences twice the curvature as does mass. And I showed actually the stress tensor above that we just calculated very simply through multiplication. Okay, so above are 16 terms representing the stress induced by momentum flows through space-time. Remember, we started with a four momentum that has 4 components. And if you were to take those components and square them, and etc., and you get the square, it's going to be equal to the total momentum squared then, and you take the square root, you get the total momentum one direction, right? Like I'm saying, the momentum only goes really one direction in space at a time. It goes also in time. So if it's fast enough. The Earth and us also is moving at the speed v1 equals c. So we're all moving through the vacuum and propagating basically very similarly at the speed c. And the Earth and us also is moving at the speed v1 equals c, perpendicularly. Again, remember that gun shooting a sign. Perpendicularly through the plane, the sign, perpendicular to the direction of motion of the bullet going through the sign. Okay. The momentum flow through this plane is me times c, and the corresponding energy density is mcc divided by v. We know that this energy density produces a curvature in the time direction equal to, I say the curvature is equal to 8 pi g divided by c to the fourth divided by 2 times mcc divided by, that's the energy density, is equal to 4 pi g divided by c to the fourth times mecc, which is basically the energy divided by the volume energy density. Okay. So, looking at this, yes, curvature, that's true. What 8 pi g, look on the top here. There's a tendency for things to seem complicated when they're really, really simple. So let's come back to ground ourselves here. 8 pi g divided by c to the fourth is equal to, I've taken you through this so many times in this 4 presentations, and we're going to have 5 presentations before we're done. 8 pi g over c to the fourth is equal to the curvature in space-time induced by mass divided by the energy density. So if you multiply the curvature divided by the energy density, if you multiply that times the energy density, of course the energy density that you're multiplying is a numerator, like over 1, right? Energy density over 1. Now you take the numerator and the denominator are both energy density, so they both cancel. You're just left with the curvature. So that's all I'm saying here. I'm just saying that's the power of this constant k. It can convert mass density or an energy density into curvature. And then if you invert it and multiply the curvature, you convert the curvature into mass or energy density, depending whether you put c to the fourth there or not. So powerful, simple. So light, on the other hand, travels equally through distance and time. Thus, in the frame of light, the momentum of the Earth is moving perpendicularly through a plane perpendicular to time. So we have the Earth rocketing through like a bullet through a sign, but we normally have time going in the upper direction. So But let's rotate it this way. So it's a bullet going in through the plane of the sign, and it's a plane perpendicular to the direction of the bullet, and the bullet in this case is the Earth, and it's going in the direction of time. So and that going a bullet going through a plane perpendicular to a direction produces curvature in that direction. So let me just say that. Thus, in the frame of light, the momentum of the Earth is moving perpendicularly through a plane perpendicular to time, with a momentum of the mass times the speed of light, and also perpendicularly through a plane perpendicular to one of the distance directions with a momentum MEC. Okay, so it's going, as we measured earlier with the inductance and capacitance of free space, when we modeled the circuit, it goes in the same amount of distance in time as in space. So it's going to curve both equally. So these two momenta ensure that for light, the direction of time transit is curved and the direction of distance transit are equally curved. So light, being faster in the Earth's gravitational field, experiences the curvature of time and the curvature of space. Now, it's not just light. Light is not that special. That's why in the beginning I measured space with got the induction of the vacuum, and I measured space and got the induction of the capacitance of the vacuum, because it applies to anything moving through a waveform through the vacuum. It'll travel at speed of light, and it'll go equally in time and space. Okay. So so that's basically it. For light, it goes, and also I want to talk. Remember that cathode tube, the electron, was also going fast enough that it was going equally in time and in space. So it has twice the acceleration that Newton would measure with a rock. Just the electrons traveling in the cathode ray of an earlier TV or computer screen. Okay, so we've talked about that probably enough. Okay, so I'm going on here again, and I always want you to see this expression, curvature over density equals 8 pi g divided by c to the fourth, or c squared. You probably, if you've watched this far along, you're probably dreaming this in your sleep. Yeah, you might not ever forget it, which would be a good thing. So revisit. Okay, so I'm looking at this. It looks very similar to the previous one. All right, light. Okay. All right, this is different. Okay, I've said before that the vacuum is inherently two-dimensional, and we have been presented here with a four-dimensional vector. Was my statement incorrect? So I was saying that motion in the vacuum is inherently two-dimensional. And if you look at the, we talked about a four vector. Remember the momentum? We had four components. So you say two components, four components. That could confuse someone. So I'm saying, well, was my statement incorrect? Let's think it through below. The time direction for an observer is set by the direction of the momentum vector of the mass of the observer, which we call the time direction. So in other words, remember that green line? We're on that line. That line could point in any direction. And when we're riding on that line, that direction of motion we call time. That's what is time for us, right? But it's not the same time as for someone riding on that blue line observing us, because in the blue line, that's their time. I mean, the clocks obey that because their mass is traveling on that line. So The time direction for observer is set by the direction of the momentum vector of the mass of the observer, which we call the time direction. I mean, that's an explicitly correct and accurate statement. It's like a mathematics, but in English. So this is established and is not arbitrary. The direction of the other spatial coordinates is, Cartesian coordinates, is arbitrary. The swarm of particles is moving through space with a forward velocity. Its time is also aligned with the direction of its velocity vector, in Einstein's case, x4. And our time, if we are the observer, it's going to be our time direction as well. In one frame of reference, there are 4 non-zero components of its forward velocity. However, we can select our x-coordinate or any other coordinate of our choice because it's our Cartesian frames, and we can orient it however we like. However, the time is going to be the time that we happen to be moving. Our mass is what the direction that we are moving. That whatever that is, that's going to be our timeline. So that'll remain. In one frame of reference, there are 4 non-zero components of its forward velocity. However, we can select our x-coordinate to completely align with our velocity direction. So we're aligning our coordinates to one direction, the velocity of the swarm of particles. Okay. So let's look at what that means. So in this case, I took our expression that we just multiplied previously, doing the same thing again. It was easy before. It'll be even easier the second time. So look at this. I have now that you got the time direction v1. I'm using our convention, not Einstein's convention here. And we got and I'm using that because I'm doing a geometric drawing, in which case C is automatically balanced. C is equal to 1. You don't even have to worry about it when you're doing geometry. It works out that way. And I'm not using Einstein's convention. We'll talk more about that later in this chart. So we have V1 and we have V2 that we've aligned with the direction of the swarm of particles. Now, we in this chart, the direction of space in this diagram for the machinery or the person moving along the green line is the spatial direction relative to the person moving or machinery moving on the blue line is this direction BG, and I even call it there delta x2. So delta x2 divided by delta x1, which is the time according to the person riding on the green, because that's our observer in this case. So delta x2 is the distance divided by delta x1 is the time. That's like meters per second. That's how we measure speed in our when we're driving our car. We're pretty used to that. So so it's bg. The velocity 2 is bg, that distance, delta x2 divided by delta x1, which is hb. So I write that down, bg divided by hb. It looks complicated at first, but it's so mind-bogglingly simple. So anyway, you see remember I said I'm trying to train us to always see what it means. Have a picture, an accurate representation, and then we have a little bit of arithmetic, which is fine, but I want us to be able to see it. And here we go. So what we get when and the other two components, because we aligned our V2, the X2, it might be time X, Y, Z, is one way of looking at it. So this would be the X direction. We align it along the direction of the swarm that the particles are moving, which is along this red line the spatial direction according to the guy riding on the green line. So that means that the other components are zero, because you're lined all, you got all the motion going along one component, one Cartesian axis. The other Cartesian axis don't pick up any of the motion in flat space. So, and this is we're assuming it's this swarm of particles is not large enough to have distort space enough to begin to matter to us, as in matter, not matter as in mass, matter to us as in importance. So we get that. We got the velocity components are now v1, v2, and 0. And we got the boost factor the same. We haven't changed its velocity. And so then we do the simple arithmetic multiplication. I'll do it again. v1 times v1, and v1 times v2. There they are represented. First row. Second row, I'm going to do plus. We're just putting it in a table. We make it neat. So we now we go v2, v superscript 2 times v1. There we go, v2 times v1 and v2 times v2. There it is. Now the rest is 0 times blah, 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 blah. And you got a bunch of zeros. And then the last one's 0. 0 times a bunch of them. Next row is zeros, and the row after that is zeros. So, okay, so this is above. It's the same situation as before. Remember before we had the tensor, and I'm circling here in that rectangle above near the top, but down of two rectangles. So that's that tensor, right? And then we reorient the axes, and we get this thing. You want to see this red arrow pointing? A much more compact representation. So I say the above is the representation of the situation showing a minimal number of non-zero components. So a minimal number of non-zero components. A great simplification. And so that's very interesting. And this shows a stress tensor. When what this, I'm bringing up an important point here for understanding the stress tensor. If you rotate the axes of the that you can do, spatial Cartesian axes as a choice, except for maybe the time direction, you get different components, and that's okay. I mean, that's the way it is. Like if you take the Lorentz transformation, I always like to point the x direction and the direction of the motion of whatever it is, a rocket ship or whatever, and it greatly simplifies the arithmetic, let's say. But if you just have the general case, you don't align one coordinate with the motion, then you get a whole bunch of other terms showing up, and it looks really messy. Remember we derived earlier in presentation 2 and 3 really in full. The Lorentz transformation, it was so simple. It was like almost obvious the way we did it. Well, it would be a little more cumbersome and tedious, and if you didn't align the axis like I did. So, and this is not a trivial point when it comes to the tensors. You have to understand that in order to understand some of the variations that you're going to see for this. You have the same phenomena, and you got different stress tensors representing it, and it's just different views on the same situation. And this brings up something I haven't said, because I at this level I want to reproduce Einstein's work and understand it. But what we're just showing is that you can have different representations for the same physical phenomena. So the representations at some level are representing the same reality and physically are the same. So there's a you can use these things to, what's the word to use? It's something that doesn't change, an invariant. you can represent invariance and have the same things that do not change as you change the reference frame. The meaning of the things, the totality of it will represent the same thing, and that's a lot of what relativity is doing, looking for what doesn't change, looking for representations of the one physical reality that has to match in all the different reference frames and expressing it with one expression. So I don't want to go into that too much. You can see it's better, I think, to start and populate the terms, understand what they mean, understand what happens when you shift the reference frames around. And you get a thorough footing at that level, and also to be able to see what's going on and understand where they come from. And then later on, you can be thinking about it and be ready to talk about these. It seems a little bit more abstract at this level, but later on it won't seem abstract at all. So remember, I put the axis along the x-axis along the direction of the swarm of particles, which is actually the distance direction according to between the guy traveling on the green line and the guy traveling on the red line. The blue line. And the distance between them goes according to the guy traveling on the green. It's all relativity. It's always relative to whatever. Is the red line. Okay, so we align the axis, the x-axis, to go along the red line there. And the guy who aligned it was the guy on the green arrow. Okay, we aligned the x-axis to go along the red line, which is the distance axis for the guy who's riding the green arrow. So I want to show what that means in terms of the stresses. That remember we just worked out the possibilities, which produces the stress tensor. I don't like that term so much, but there it is, simple thing. And then we with the aligned axis, of course, it became even more simple. Most of it's zeros, but we do have these 1, 2, 3, 4 terms, and it's a stress energy tensor. So where are the stresses and the energies? I show you. I want to show you everything. So there it is. And these are, we've talked about it before, I think, but these elements, it's an ordinary stress element. And you see here that this one says the stress, I guess the cross section. In this case, it would be the momenta traveling through cross section at z. So remember we talked about a sign and you're shooting a bullet through the sign. Well, you orient the sign so the sign is perpendicular to the z direction, and the bullet, the swarm of particles, which could be a bullet. I'll freeze it. Remember I said it could become a solid, so it's a solid now, and it goes through. It's a bullet. That's what this is, and the sign is perpendicular to the z direction. And when you do that, and reality is four-dimensional, and you take a cross-section. So the z, when you take a cross-section of z, you cut the 4 dimensions. And if you had a 4x4, I say 2x4, but it's not. It's 4x4. What do you call it? Piece of wood, and you cut it. And it's a 3-dimensional object. You get a plane, but that you cut it at a particular length along the 4x4 and 4 inches by 4 inches. You cut at a certain length, right? In the plane of the cross section, that length is not represented. It's going to be height and depth, right? So you don't see in the cross section, you don't see the dimension where you made the cut. It's not part of that physical object, which in a 4x4, when you cut it, it's a physical plane, you don't see the length L represented in that plane. A very simple concept, but I'm trying to, it's new kind of thinking. So anyway, in this four-dimensional cross-section was, you cut a line, you get a dot, right? You cut a plane cross-section, you get a line. You cut a three-dimensional object like a 4x4, cut it. You get a two-dimensional, you get a plane. So you cut a line, you get a point. You cut a plane, you get a line. You cut a three-dimensional object, you get a plane as the cross-section. You cut a four-dimensional object, you get a three-dimensional object as the cross-section. So here, and it won't, that cross-section will not include the dimension of the cut. So we're making a cut at Z. You're not going to see Z in the three-dimensional cross-section. So I got dy, I have dx, and I've got dt on the first one here, lower left. No Z, okay? Because that's where we made the cross-section. Now, next over to the right, we make a cross-section at y. Now, we're not going to see y there. If we did, it's a mistake. But we're going to see delta z, delta x, and delta t, okay? In the first one, we had delta y, delta x, delta t. Now, delta z, delta x, delta t. These are real things. Like our mind is always making cross-sections. That's how it works. Our mind is making cross-sections in the time direction. 1, 2, 3. And what we're getting in our cross-section of this four-dimensional reality, these little snapshot cross-sections in time, is the cross-section on the far right there. Now, it's a cross-section in the time dimension. We're not going to see time in our three-dimensional cross-section that results. And look, delta x, delta y, delta z. Now you have a cardboard box that has length, depth, height. We don't measure a cardboard box by the time as part of the physical coordinates or Cartesian system that describes a box. That's our reality, and it's produced by the way our mind works. But physically, when we talk general relativity, we have to represent all the cross sections because they're all real. So in this case, okay, so we talked about y. Now let's do a cross section through x. Now what are we not going to see in that cross section? Well, I know you already know the answer by now. We're not going to see x when we do a cross section in x. So it's going to be delta y, delta z, and delta t. So let's look at it. Delta z, delta y, delta t. Great. So that's what this system is here, and it's very, very powerful. We can see in four dimensions. Human mind can see in four dimensions. No problem. You know, our retina is two-dimensional, and we think we see in, well, we do see in three dimensions, but we don't really, because you can paint a cube, for example, each face a different color. When you look at a cube, you're only going to see 1, 2, 3 faces out of the 6 faces. You'll think it's let's say black, red, green, right? Cube, because that's all you see, black, red, green. But you might on the other side have purple, yellow, orange. You won't know anything about it. We don't see in even 3 dimensions, except our mind pieces it together. Well, our mind can easily piece together 4 dimensions as well, same way, through the cross sections. That's what I'm doing here. Good. Just check that I recorded it, so don't want to lose it. So what I've shown is that we lined with the direction of the swarm, and what I want to show what they represent. So in the first term goes, you follow it down my green line there, it goes over to the delta x, delta y, delta z, the time cross section. And we have, this pressure in the time, this pressure in sub tt. So it's pressure in our physical delta y, delta x, delta z, there's a pressure from the mass component there traveling up through time. We get a pressure in the cross section. Wow. Okay, so let's look at the other two. V1, V2, V1 here, that purple, I put it in purple, follow the purple line down. Oh my God, and the other one, V1, V2, and the V2, V1. And look at them, there they are. It's like a shear stress. Wow, we got two shear stresses. The shear stresses oppose each other, otherwise the thing would rotate and we get terribly dizzy, but our reality doesn't rotate because the shear stresses oppose each other. Okay, so then we have the other one is a V2 times V2 component. And we follow the red line down there, and it's V2 times V2 that's going to be x, right? And so we're not going to see x in that box. And we got delta z, delta y, delta t, no x. Good. But we have a stress and the xxx inside that particular volume element, okay? Wow, so that's, you might want to take a screensaver or something and keep that around, look at it a few times. It's new, anything new, you know, it's like go to a new city, you get a new subway route, you're not going to look at it once and take it all in any way that, unless, well, there's some people that can do it, but I know myself, I need to look at it a few times. So you can always do a screensaver. By the way, if I'm going too slow, and sometimes I do that on purpose to have things sink in, you do have control on YouTube. You can speed it up. You can make me go, I love it when people make me go 2 times the speed. I seem so smart because I talk like this, so fast like this. So yeah, do that. I don't like it so much when people slow me down, so I see. Anyway, I'm getting silly. Yeah, that's one of the things that happens with you get happy, all this stuff. So let's see. This moving swarm of particles turns out to be a very fun toy. And yes, it is. I'm having fun. I'm making jokes. It really is fun. So let's explore the full extent of the curvature that can be produced by sending the swarm along all of the 3 cardinal directions. Like I'm going to send out 3 swarms. 3 different swarms all at once, and I'm going to put them one on each of the cardinal dimensions because I say cardinal, but it's like x, y, z, so it's Cartesian, I guess, but it's kind of so related. Anyhow, I noticed it here. You go back. Let's go back. Notice that it only, look in the center there, the tensor. It only has 4 components, and the rest, that's of 16, so the other 12 are 0. And what I'm going to say, well, what happens if you, that's for one swarm going in one, where you're lined to the x. What would happen if you took, what did I say, 4 swarms, and you, or did I say 3? That's what we're going to do here. Okay. 3 swarms, yes, that's what I thought. Okay, so you take 3 swarms and send each one on one of the Cartesian directions x. You send the other one going y and the other one going z. Can you populate the stress energy tensor with stresses when you do that? So let's see. Let's do it. Best thing is to try it out. So here we are. Okay, I did it. So I got the first one, which we already did. See that red arrow on the top? And let's do V3. So of course, that one's not going in the V2. This is a second swarm, but it's going in the V3, which might be X, Y, in the Y direction. And we do that, we get the tensor for that. It's like, oh, it skips a row because the second term is 0. Then you get in the third row, you get something in the fourth row. That's good. Okay, now let's send out another swarm in the x, y, z, x, y, z direction at the v3 velocity. So let's do that down here at the bottom, the arrow pointing to your right. You're right. That sounds nice. May it be so. And we do the multiplication and we get the first row populated. And then we get the last row populated. Okay. Now, it's physical reality and we got three things going on at once. The stress tensor for that should be, you should be able to combine them all. I don't know any reason why not. You know, if I ever make a mistake in any of these things, I hope whoever sees it sends it to me so I can fix it and then redo it. Yeah, but I think it's right. Be interesting. I'm always, you know, science it's not about being dogmatic, and Einstein wasn't right all the time. Far from it, especially at the beginning. It was kind of miserable. But let's look at this thing. So I combine them all, and I'm thinking, you know, you'd think, oh, I've got three Cartesian directions, three masses. You'd think it was going to fill up the whole thing. And I look, oh, and I find out, see in the bottom here, it says cannot twice. I must have been really frustrated. I'm going to take that second cannot out. Cannot produce these three shear stresses. See these here in the balanced. There's six, but three. They're always a balanced pair. So cannot produce these three shear stresses moving three masses along the cardinal directions. That's actually true, I think. Notice I oriented my Cartesian frame with so it goes along the three different motions of the swarms, and under that circumstance, it's like I've used the frame where everything gets simple again, like in a special relativity by aligning my x-axis with the motion of the particle in my x-axis along its motion that I'm as I perceive it in my frame. Then the Lorentz transformations become very simple. Well, here's a simplified view, and it in that view there's no these. I'm missing three shear stresses. Okay, and so that's that. Now let's continue on here. All right. So what does that mean? I'll move myself over a little bit. There we go. We just worked out what the components of the stress tensor are when you send simultaneously three swarms of particles at once, each along a Cartesian axis, namely along x, y, and z and t. It's one way of saying it, and found that we cannot produce six. It's still too far over there. Okay. Still, we cannot produce six of the shear stresses with this approach. Yet, we found earlier that we could produce these six shears as well as the other components when multiplying an arbitrary momentum having four components. So, we've produced a kind of paradox. Now, the beauty of a paradox is it shows that we're about to learn something really cool. Because the physical reality is physically real, and I don't think we've made any mistakes. So if I did, I would have corrected it. Okay, so I just so anyway, yeah, and here I'm showing what we produced before. Remember, the stress tensor was filled up. I can go back. Let's see, where am I? I'm down here. All right, so I'm not gonna. I'll go forward. So there it is. So we compare the two. We have the stress tensor. One way of writing is T subscript U subscript V, which represents, U goes from 1 to 4, and V goes from 1 to 4, and you get 16 components. It's just it's a word, a mathematical word. So I put it in there. Einstein stress energy tensor, because we're going to reproduce Einstein's field expressions quite completely. Although relativity is a big subject, you can spend your whole life on this stuff, but I'm going to give you the insight without all the needing all that stuff. So you see that the two our representation where we aligned at our axis has the 3 and another 3 shear stresses, and we know there's shear stresses because I showed you on that chart. You can go back and look at it. Hopefully you did a screen save. I'm going to, by the way, I'm going to submit this presentation as a paper in ResearchGate, and you can be available. You can join ResearchGate if you're not already, and look up the presentation, and then hopefully watch my explanations, because I'm not sure whether a person can just look at it without the talking to the presentation to really get the feel of it, because auxiliary ideas that naturally are brought out when a person talks. Anyhow, that's that. So we have to conclude that the 6 strain stress components that are expressed above are artifacts of frame misalignment. It's like, oh, what do I mean, frame misalignment? Well, we know we had to align the frames along the Cartesian, so that the Cartesian axes lined up with the motions of those 3 particles in order to get this result, right? So what if it's not aligned? Well, if it's not aligned, generally you get the large tensor on the right-hand side. So we can easily prove this since there's only one swarm moving. This means that we can easily align one of the cardinal directions of the measurement frame, such as x2, superscript 2, to align with the motion of this one swarm of particles. We've already modeled this and we've already obtained the result below, so I'm just repeating that. Now, I want to bring up, if you do mechanical engineering or even civil engineering, you're going to run into, hopefully, the Moore's circle in two dimensions, and it represents a 3-dimensional stress element, which is, it's a conceptualization because these elements are not oriented in these particular ways in the material, but it's a way of looking at it and analyzing the stresses as you rotate these things. Well, if you start with Moore's circle, and it's just a name, it's just a 2-dimensional stress element, okay? And you have 4 principal forces like compression on the top, top and bottom. You got tension on the 2 sides. I mean, that's not complicated. I mean, I can do it. I can do it with my mouth. Do it with your freaking body. I mean, make it tangible. Make it part of yourself. It's simple. Okay, but notice I only have four principal forces. But if I wrote on the right-hand side here, that was the left-hand side. Right-hand side, if I rotate that by 45 degrees, the components of the forces, same forces, get broken down into 2. So one smaller force pushing in at, I can never, there we go, pushing in at an angle, and smaller because there's another component of that one force that's going now along the surface of this stress element. So you go from 4 normal forces to 4 principal forces to 4 normal forces plus 4 shear forces and the 45-degree angle rotation, right? So we just showed that it's not unusual at all for when you rotate the Cartesian coordinate system to have the principal forces suddenly gets change and different shear forces to pop up out of nowhere. In this case, 4 of them, and that's only 2-dimensional. What about 4-dimensional? So part of understanding the stress tensor is to understand how its description can depend on the the coordinate system used to define it. But it's the same reality. All right. So, I've been doing this for over an hour now, and it's turned out to be longer than typically people can maintain their concentration and get a little tired. So I need you fresh. I need you fresh for the next, the funnest one of all. We're actually going to just build the stress tensor. And it's quite awesome when you do that, especially this way, because you have a good understanding of what everything means, and you have the images, which are not fanciful images, they are representing physical realities. You have the images to put in your mind, as well as the simple arithmetic, in such a way that it's easy to remember. I love this thinking, because a lot of my thinking, a lot of what I do, I don't know if I should admit this, but it's not reading textbooks all the time. I basically go to sleep, and I see all this stuff in my mind. And one of the reasons I can see this and think in my sleep is and do the most of my work is actually to fall asleep. I guess I'm a lazy son of a gun, right? But you can't get any tireder. Right? You know how when you do physics, you go, oh, it makes me fall asleep. Well, most people just forget about it then, but I'm quite happy when my eyes cross and I fall asleep, because then I'm asleep. You can't get any more tired, right? So you have the strange situation where you're already asleep, so it can't fatigue you anymore. Then you can go ahead like snake or something, whatever the word. You can go with great. You can really do your physics, and you get tired while you're asleep. You can't, you're getting rested. So not as rested as you might think. Anyhow, we got this to look forward to the next time, and it's going to be so great. And I do want you fresh. So we're gonna end that here. And thank you very much for watching this. It's been a real thrill. Thank you.